All right, welcome to day 3 of the GTC 2021. Today, we're very pleased to have Danny Ruberman here to talk to us about the diffeomorphism group of a four-manifold. Thanks, Danny.
So thank you very much. The Georgia Topology Conference is one of my favorite conferences, probably maybe the first conference I ever spoke at outside of graduate school when I finished, and still sentimental and favorite, and always a great affair. So it's particularly fun, fun to do it in these peculiar circumstances. But someday I guess we'll all be back in Athens and we can be together. Anyway, so this is a joint project with Dave Auckly. That's I think you may have heard a similar talk before, but I'll try to throw in a few different features to keep it varied. So let me just give a little bit of background, because this is what I have to say is mostly about four manifolds, but the topic really goes back further. And so let's start just briefly with talking about a general smooth manifold. So for a smooth manifold, of course, you can study the topology of the manifold itself, but an interesting, if you like, invariant of the topology of a manifold is its diffeomorphism group, which has a topology itself, or its homeomorphism group. Those are one sits inside of the other, obviously a proper subgroup. And these are, of course, they're actually interesting as groups. That's in some sense related to the topic, more related to dynamics and other things that we won't be dealing with, but more to the point for me is that they're interesting spaces. The diffeomorphism group is an interesting space and has interesting topology, and likewise for the homeomorphism group. And it's interesting; they're interesting to study in and of themselves, and also to just compare. So let me. And when I say the topology of these spaces, I mean the topology as maybe their algebraic topology, the homology or homotopy groups. Well, the simplest algebraic topology invariant that I can think of is simply the number of components, or H0 or pi 0, if you like. And this kind of the first example that I know of that shows that there's something possibly interesting there comes from Milnor's exotic 7-sphere. So I imagine most people know this, but that's a smooth smooth 7 manifold that's homeomorphic to the 7-sphere, but not diffeomorphic to the 7-sphere. So actually, when Milnor constructed it, his original construction, he came up with something that was homotopy equivalent to the 7-sphere, and apparently he originally thought he had found a manifold that was not homeomorphic to the 7-sphere, but then he, I guess, thought a little bit more about it and realized that in fact it was homeomorphic to the 7-sphere, but not diffeomorphic. And the way he showed that it was homeomorphic to the 7-sphere was to exhibit his manifold, which was built as a sphere bundle, a 3-sphere bundle over the 4-sphere, I think, if I got it right. And then he kind of rearranged that. We would sort of say he rearranged the handles in retrospect to exhibit that manifold as the union of two 7-dimensional balls meeting along a 6-sphere. So you might ask yourself, well, why doesn't that show that it's that this manifold is actually diffeomorphic to the 7-sphere? And the answer is, well, if you because of course the 7-sphere is itself written as a union of two balls, as we all know. And if you like, the 7-sphere, if you think about the gluing of the upper hemisphere to the lower hemisphere, they're sort of sitting there inside the 7-sphere. So we can sort of think of that as essentially the identity map. For this other exotic manifold, it's glued by, well, all he showed was that there were two codimension 0 submanifolds, each diffeomorphic to a 7-dimensional ball. So when you identify those with the 7-dimensional ball, that gives you some, if you like, automorphism of the boundary, or diffeomorphism from the 6-sphere to the 6-sphere. And the conclusion from his brilliant proof that this sigma is not diffeomorphic to the 7-sphere is that, in fact, this diffeomorphism of the 6th sphere, the gluing map, can't be connected to the identity map by a path of diffeomorphism. So these days we would say it's not isotopic to the identity. So just again, to basic terminology, a path in the diffeomorphism group is called an isotopy, and a path in the homeomorphism group is called a topological isotopy. At least that's what I would call it. So there's no real standard notation for isotopy, but this little squiggly line, that's supposed to be my symbol for isotopy. And if I want to say it's only the isotopy consists of homeomorphisms, that would be a topological isotopy. So those of you who are newish to the subject might actually wonder about whether that path itself has to be smooth in T, and the answer is no. But that's a kind of a subtle fact. Okay, well that's an interesting fact about that. So this phi is not connected to the identity by a path of diffeomorphisms, but actually Alexander showed way back in 1923. So we're approaching 100th anniversary of this, of what's called the Alexander trick. In fact, says that phi is topologically isotopic to the identity. So that's a really surprising and interesting fact. And if you want to phrase it differently, and this is kind of the way I'm going to phrase the theorems that I discussed today, that this phi represents a non-trivial element in the kernel of the map from on pi 0 induced by the inclusion of the diffeomorphism group of the sixth sphere to the homeomorphism group of the sixth sphere. Okay, so those are, or if you like, if you prefer, I could have written here instead of pi 0, I could have written h0, because those are essentially the same thing. Not quite. Okay, so well, I'm not going to review the past 60 years or 65 years of high-dimensional topology, but let me briefly summarize it to say that although in general these groups are not computed completely, they're actually fairly subtle. There's an awful lot known about the homotopy groups and homology groups of the diffeomorphism group of a manifold in dimensions at least 5. And by the way, it's easier, and it gets a lot more complicated if the manifold is not simply connected. Okay, so those are that's a fairly well understood topic, but not completely. There are still interesting questions and still serious research going on in that domain. The case of 3 manifolds is quite well understood. The case of 2 manifolds, even better, or even better studied. Of course, that's related to the study of the mapping class group and so on. And so, of course, what does that leave? Well, that where the mysteries always show up, which is in dimension 4. So some years ago, 1998, which seems like a long time ago to me, I showed that there was that there was a difference between smooth and topological isotopy in dimension 4. So the theorem that I showed was that there's a simply connected form manifold, not a particularly exotic one, and there are lots of new interesting examples these days. But there's a simply connected form manifold and a diffeomorphism, orientation preserving, that's not isotopic to the identity. On the other hand, not smoothly. So again, when I say isotopic, I mean not smoothly isotopic to the identity, but yet it's topologically isotopic to the identity. And in fact, if you like, usually pi 0 of a space is just a set, or a set with a distinguished point in it, because you pick a base point. But because we're in a topological group, or pi 0 is a pi 0 is a group. So in fact, this alpha is that I cooked up is of infinite order and it lies in this kernel. And I didn't think of phrasing it at the time, but I could have at the time, obviously, just for trivial reasons, could have said the same thing would have applied to, instead of saying pi 0, could have said h0. Okay, so the question that occurred to me really immediately, and that I put in some effort at the time, I'm not particularly successful, although it bore fruit years later was, could you do something similar for higher homotopy groups? Or, and again, although I didn't think that much about it, for higher homology groups. And that's what Dave and I have done. In fact, Dave and I started talking about this really on the spot. We both gave talks at one of the birthday conferences for Rob Kirby, and I gave a talk on my result, and Dave gave a talk on related things in four manifolds, and we started talking then, and really continued on for the next 20 plus years, searching for essentially the result that I'll talk about today. So, so the theorem I want to talk about is says for any k bigger than 0, and r and any r, there's a simply connected four manifold. So Z, so here's just, for notation, Z, K, and R, with the property that the kernel of the map from the kth homotopy group of diff ZKR to the kth homeomorphism group of ZKR contains a free abelian subgroup of rank R. In fact, actually, I should have written here, so let me squeeze that in. So in fact, a summand of rank. So if you like, you learn a little bit more about the group theoretic structure. So these manifolds, by the way, are quite standard in the sense of they're rather simple in the world of four manifolds. They're all diffeomorphic to some connected sum of CP2s and CP2 bar. CP2 bar, as I'll discuss in a little bit, is CP2 when I think of it as an oriented manifold with its complex orientation. CP2 bar meaning just take the other orientation. Anyway, there's some large number of summands proportional to the K and the R. So K is the sort of the dimension of the homotopy group, and R is just telling you how big a summand. So to get bigger summands, you need, at least by this construction, you need bigger R's. And in fact, this whole summand survives into homology. So in fact, the summand that we construct actually is non-trivial in the homology of the diffeomorphism group. So again, we could have replaced all these pi's by pi case by h case. That's actually it took a little bit of doing, and that's one of the things that's delayed the appearance of our paper was trying to get the homology result pinned down. There's some little, it's not technical difficulties, it's just finding the proper formulation of that result. In fact, there's a reasonable conjecture that instead of saying Z, instead of finding a subgroup of rank R, so for any given R, you can find some manifold where with this Z to the R summand or Z to the R subgroup, we can find. So I would conjecture that you should be able to find a free abelian a group of infinite rank as a subgroup of the kernel, or maybe as a summand of the kernel, either in homology and homotopy. Just maybe I should say as a remark, if we define, well, let's see, I think it's these days we would call it T diff. So T is somehow for the like the Torelli group, the group to equal the set of diffeomorphisms from, so I guess this is a Z to Z, such that that act trivially on the homology. Then in fact, I showed a long time ago, so it's sort of the following year, maybe 1999, that if you take pi 0 of T diff, well, again, the kernel this contains a subgroup of infinite rank. But if you think of, and actually in the abstract of my paper, I wrote that in fact pi0 of diff contained a subgroup of infinite rank. But of course, that's not what the paper says. I don't know. I guess that was why I think I was under the illusion that was the case, and didn't do a good job of proofreading when I when I wrote the abstract. In any case, so
Z here is.
Again, the same Z. Similar collection of Z's. Yeah. By the way, there are so this sort of maybe if you're interested, or maybe if I remember, I will make a quick remark when I talk a little bit about the method for detecting these results, for detecting these elements. So the whole point of all this is that I'm going to show you some way of detecting elements in these homotopy groups or homology groups, and that uses some gauge theory. And if you use a somewhat more sophisticated version of gauge theory, you can actually detect this infinite rank subgroup. And that's an interesting. There's an interesting technical issue that comes up in trying to do that for the higher homotopy groups or higher homology groups. So if time permits, I will make a comment or two about that. Just a couple of extensions that kind of come. Well, actually, the first one doesn't come for free, but an elaboration of the construction. I'm sorry, let me scroll back. In the statement here, it's for each homotopy group, you get a manifold ZK. And a couple of times when I gave talks about this early on, people asked, well, can you get a lot of different homotopy groups for the same manifold? And we can kind of do that. It's not quite the result, not quite optimal, but you can find some other map. So now it's a P instead of a K, and it's a superscript instead of a subscript. Anyway, there's manifold ZPR, where you get all the homotopy groups in one parity between 0 and P. You can get a Z to the R summand. So as the statement reads, so the kernel on, and again, same thing for homology. You can make the kernel on pi j for the same fixed ZP be large. In other words, have a big summand for all j congruent to P mod 2. So you sort of get every other one. So I don't know how to get all the homotopy groups in between 0 and P, and I don't know. I imagine it's doable. It's just we haven't come up with the right setting for that. Anyway, there's sort of the method just sort of dumps this silly parity condition in our labs. And again, this is more for people. There's a sort of a generally nice connection that occurs in lots of circumstances. As we saw in Watanabe's work, there's an interesting connection between spaces of embeddings of surfaces or submanifolds and spaces of diffeomorphism. So here's sort of a sample theorem that you could say that. So if you were interested in the homology or homotopy, actually, sorry, by the way, this one is only about homotopy, not about homology, just because there's some fibrations, and this is somehow coming from the exact sequence of a fibration. If you look at the space of embeddings of a two-sphere in a particular homology class that shows up in one of these manifolds, or a slightly enlarged version of one of these manifolds, then that space of embeddings has large homotopy groups as well. And all of those, so in other words, this Z to the R subgroup, and if K is not equal to 2, it's actually a Z to the R summand that vanishes when you pass to the topological category. So you do learn some extra things, and that one just sort of falls out of the construction. That one is sort of for free, but you just have to say it. And the restriction to K not equal to 2 is a little funny. That's again, this is, I guess, why it's good to write papers, because you notice these things that you thought were true, and you realize, oh, there's a little hidden assumption. So anyway, that was so there's those some extra extensions and variations on the same theme. Okay, so let me briefly sketch the proof. I think this diagram may have appeared in another talk or two, just which is that there's sort of two sides to it, and they're sort of different. And the one on the right is how to detect families of diffeomorphisms, and that will be done by parameterized gauge theory. And that's the same method that I used in the back in 1998 and to detect the pi zero. And at the time I knew in principle how to do the part on the right, how to define invariance. Maybe even said so in the paper that I wrote. So but the challenge was sort of twofold, which is to construct things. So sort of the second big part, which is really the new part, is the construction of the families of diffeomorphisms. And again, it's constructing them in a way so that the detection results would apply. In other words, you have to, there's lots of things you can construct, and the only question is, can you marry the construction to the detection result so that it actually says something. And there's an interesting overlap between these, and I will spend a few minutes talking about that shortly, which is that in both settings, both in the construction and in the method for detecting families of diffeomorphisms, the phenomenon of stabilization, which in this setting, well, actually, this is an interesting phenomenon in all dimensions, more sort of even dimensional. Even for surfaces, this is an interesting sort of phenomenon in the study of diffeomorphism groups, where you take a manifold and enlarge it by adding on something standard. So for four manifolds, the standard thing might be adding on S2 cross S2 or adding on CP2. By the way, this last bit reminds me that when I say I'm talking about four manifolds, I really mean I'm really thinking of oriented four manifolds, so that there's a distinction between adding CP2 and adding CP2 bar. Okay, so I'm going to talk more about the constructions. As I say, that's the part that was that took us a long time to sort out, and that's the fairly new part. And as I say, I'll talk a little bit about how you detect these things. That's more technical because, in a sense, because it uses gauge theory. And any case, but I'll describe enough so that maybe you can get a feel for it. And again, just I guess I said this already, but I'm making the distinction. Want to make sure that all the manifolds have orientations, and the key point for us in that, well, that shows up lots of places, but one important point is the difference between CP2 and CP2 bar, which is just CP2 as an oriented manifold with the non-standard orientation. Okay, so here's, let me just say a sort of a first few sentences about gauge theory, although I will elaborate on this a little bit later. So the remarkable work of Donaldson, okay, and later the version for Seiberg-Witten theory, sorry, gave us invariants for which were called Donaldson invariants. So for today, those will just be numerical invariants. In other words, integer invariants of certain four manifolds, or in the world of Seiberg-Witten theory, there would, denote them as SW of X, although I don't think I have much to say on the subject today. And these are smooth invariants. In other words, if you get different Donaldson invariants, if these numbers are actually different, then the manifolds are not diffeomorphic. Although they well could be, and it was the most interesting case, of course, would be when the two manifolds X0 and X1 are homeomorphic. And there's many pairs, infinitely many, not just pairs, but infinite families distinguished by these Donaldson invariants. So here's an interesting coincidence. These Donaldson invariants, on the one hand, fail to distinguish if you take your manifold and do this stabilization, either by adding CP2 or by adding S2 cross S2, then the Donaldson invariants fail to distinguish those manifolds. So in other words, they're rather unstable with respect to this geometric operation of stabilization. Those distinctions disappear. On the other hand, the distinction between the manifolds themselves seem to disappear. So for all examples that I know, maybe others. I saw Bob Gomp here earlier, so maybe there's something if you want to correct my knowledge here. For all known examples, and I imagine there's still some interesting cases to explore. If you add CP2, so when I say such pairs, I mean if you take a pair of manifolds distinguished by their Donaldson or Seiberg-Witten invariants, and you add CP2, then they become diffeomorphic, and likewise for adding S2 cross S2. So this sort of instability of the invariant is reflected in the actual instability of their diffeomorphism classification. And again, this is where the orientation shows up. It's the case if they're distinguished by their Donaldson invariants, then adding CP2, after you add CP2, they continue to be distinguished by their Donaldson invariant. So that's I should credit that. That's of course due to that's due to Donaldson. Actually, the results. Excuse me. Both of these results here and here are due to Donaldson. Amazing theorem from Donaldson. So, by the way, it's an important observation and really a classic theorem of Wall, and well worth reading if you haven't read those papers of Wall from the mid 60s. Say that in fact this stabilization always happens if you stabilize with S2 cross S2 some number of times, and of course the tricky part about Wall's thing is it doesn't specify the number of times you have to stabilize. But as what I was saying above is that the experience shows that in many cases once is enough. In other words, one stabilization is enough. Okay, so let me show you how to use this stabilization to create some interesting diffeomorphisms. And we're going to use a little bit about CP2. So let me just remind you of why I assume I hope everybody knows these things. H2 of CP2 is the integers, and that's generated by a two-sphere, which is really the CP1. And with the standard orientation, the self-intersection of that sphere, if you make it transverse to itself and count points, the self-intersection is 1. If you reverse the orientation, well, the homology doesn't change. I'm going to change the name of the two-sphere just because there's too many things. Otherwise, there's too many things called S in this discussion. So I'll call it E, which is kind of the algebraic geometer's name for exceptional sphere. So if you change the orientation, what do? You change the self-intersection, and now it's -1. Okay, so there's an interesting self-diffeomorphism of CP2, which in fact, the way you define it, it's an involution. You just take complex conjugation on all in homogeneous coordinates. You check that respects the usual equivalence relation. That's orientation preserving. So after an isotopy, say near a point, you can assume that this rho is the identity on a ball. So of course it won't be an involution anymore, but it will be a diffeomorphism. So when I write rho, rho I will call a reflection, and reflection sort of sounds like it should be of order 2, but it's really a reflection modified so that it's the identity on the ball. And the point of doing that is so that I can take two such diffeomorphisms and glue them together on a part where they agree. So in other words, at a point where they're both the identity. Okay, so as I say, it preserves the orientation. It's easy to check that it's multiplication by -1 on homology. That, of course, is not affected by the isotopy. Well, okay, so that's on CP2, but there's a standard device for transporting that diffeomorphism to live on any four manifold, so long as that manifold has an embedded sphere. So suppose you have a four manifold and an embedded sphere with self-intersection plus or -1. Well, if the plus self-intersection is +1, you can write that manifold as some other manifold connects some CP2, and if the self-intersection is -1, then you're writing it as some other manifold X connects some CP2 bar. In any case, you get a diffeomorphism, which again I'll call rho, but this time it's rho, and it sort of depends on the placement of S. So I'll call it rho, I guess, super S, and it's a diffeomorphism that's essentially, on most of X, it's the identity. And on this part, it looks like rho, and then, well, something funny happened. We had to organize it so that those fit together well along the three sphere. So it's not going to be an involution. In fact, typically you can't make it isotopic, even isotopic to an involution. But anyway, but we'll call it a reflection anyway. So that's another kind of reflection. So I guess this is rho S. Yeah. Okay, so we're still actually back in 1998. So here's how you use these reflections to cook up, and some known facts about four manifolds to cook up an interesting diffeomorphism of some manifold. So as I say, this uses this stabilization and this sort of one-time stabilization in I think, an interesting way. So the starting point is you take just any pair you like of manifolds with distinct Donaldson invariants, and actually this much of the argument would work if I had said instead Seiberg-Witten invariants, but there's good reasons for saying Donaldson invariants that make life easier later on. Okay, so let's take these distinct manifolds. So they're different manifolds detected by this gauge theoretic invariant, and but that have the property, which as I asserted earlier, is quite common, that they become diffeomorphic when you add CP2. So for sort of technical reasons, I'm going to actually add a few more copies of CP2, but now with reversed orientation. So I'll make a manifold Z, and this Z is kind of the prototype for all of the, if you remember at the beginning when I stated the main theorems, there were a lot of Z's with sub and superscripts. They're all sort of built by some elaboration of this process. So this is kind of the beginning of all the Z's. Okay, so here's Z. Take Z is well, it sort of has two identities. One is X0 connects some CP2, so now it's sort of become something standard, and we just throw on a couple more CP2 bars. So I'm going to do this routine of adding CP2 and two CP2 bars enough times that that combination deserves its own name. So I'll call that combination N. Okay, so it takes Z, and so Z is also the same thing as X1 connects a copy of N, which, well, so if you like, think of adding in CP2 to make it diffeomorphic to the other one, and then adding the two more copies of CP2 bar. Okay, so there's this manifold, and there's a small thing you have to worry about. I really want to have chosen a specific diffeomorphism between these in such a way that, see, when you write something as a connected sum this way, the homology sort of splits up in a kind of canonical way as a direct sum. So I would like those two homological splittings to line up. So you can do that because these manifolds have lots and lots of self-diffeomorphisms that essentially move any collection of homology classes from one to another. So you can assume that when I write equal, I mean that I've chosen a diffeomorphism that makes the homologies line up in this particular way. Okay, so that actually, again, that goes back to Wall, not the other Wall paper from the era. Okay, so the thing to notice is that by adding this N, I've created a lot of spheres of self-intersection plus and minus one. So there was the S, well, let's see. So in either version, I have an S0 or an S1. I could take S plus E1 and either plus or minus E2, and then do the same thing. And those spheres are all disjoint from each other. Those just live disjointly in this N. And if you calculate its self-intersection, I get a 1 from here and 2 minus 1s from the E1 and E2. So that all adds up to -1. So that's a -1 sphere. Okay, so using the reflections, I can build two diffeomorphisms. One using the first decomposition into X0, connect sum a bunch of stuff. So I get the identity map on X0, the reflection using the sphere S0 plus E1 plus E2, and then compose that with the reflection using S0 plus E1 minus E2. And then using the other decomposition of Z, I can do a similar thing, only instead of using E1 and E2, I'm going to use and S0, I'm going to use E1 and E2 and the sphere S1. So because of the way I've set it up, the alpha 0 and alpha 1 are actually homotopic, and great theorems of Quinn and Perron from the mid-1980s say that, in fact, those diffeomorphisms are isotopic to one another. Or if you like, the composition of one with the inverse of the other is isotopic to the identity. So that was my so far that's just a construction, and then here's the theorem that says that this diffeomorphism, well, if you take the one composed with the inverse of the other, that's not isotopic to the identity. But as I said, using other people's work, very hard work, by the way, those papers are not easy to read. Those are that composition is topologically it's isotopic to the identity. Okay, so that's sort of the background from 20 plus years ago. And my dream at the time, which and Dave and I guess Dave had a similar dream, was that one should be able to sort of by, I mean, the pattern seemed very clear, and which is that, well, what you'd like to do is sort of do more stabilizations. You know, so what did it do? I mean, we went from distinct manifolds to distinct diffeomorphisms. So by stabilizing, so you sort of think, well, if I stabilize one more time, maybe those diffeomorphisms become the same, and then I can somehow do some trick to use the different stabilizations to give me an interesting one-dimensional family. In other words, an element of pi1 of the diffeomorphism group. And then if you can get that going, well, maybe you could stabilize again, and then go from pi1 to pi2 and so on. So that's basically what we've done. And as I say, it took us a long time to figure it out. Yeah. Okay. So here's so the first step actually took a surprise. Actually, in the end, well, it took also a long time, and that was done with well, again, with Dave Auckly and Hee-Jung Kim and Paul Melvin and I. And I think the results a little bit earlier, but it took us a while to write it up. So from 2015, what we showed was that if you took, so remember that this is referring to that same example, take the sphere S0, so that sphere of self-intersection 2, that sphere S0 is isotopic to S1 if you stabilize one time. If you stabilize it by S2 cross S2. I should say by this also, the results also due to Selman-Akbulut. In some sense, it's kind of embedded, implicit in older work of Selman's, but you sort of have to think about how to get from the situation we're in to apply what Selman had done. So, but in any case, it's so this is a result we should have proved well before this, but for whatever reason, it took us a long time to figure it out. In any case, so if you add a single S2 cross S2, those spheres become isotopic as just as submanifolds, and but a straightforward observation is that if you take oh, I guess here I've written it already. If I take CP2 connect some S2 cross S, sorry, if I take S2 cross S2 and add one more CP2 bar, that's the same thing as adding CP2 and 2 copies of CP2 bar, which was this manifold N. So if you like adding this, if you add this N, then S0 and S1 become isotopic. Okay, so that's a statement about the spheres. But since the spheres, so just to go back to the definition here, since the diffeomorphisms are built out of those spheres, it follows that the corresponding diffeomorphisms are isotopic. So as you sort of imagine moving the sphere S0 to S1 after adding one more copy of N, then you can actually do the reflections as you go along. So in other words, that gives an isotopy between the diffeomorphisms. So by the way, since I'm sure I won't get to the details of it, that's the sort of nature of the that's sort of the related to the fact that that's how you see facts like the relation between diffeomorphism groups and or homotopy groups of diffeomorphism groups and homotopy groups of spaces of embeddings of submanifolds. Okay, so here's how we're going to use this, and this was sort of the second step. So as I say, you get this isotopy between the stabilized version of alpha. So alpha added on where you add on the identity of N. So that's that results from the work of the 4 of us, and so we get an isotopy between alpha stabilized and the identity stabilized, and so let me just call that isotopy F sub T. And so here's the idea. So then that isotopy is going to give us an element in pi1 of the diffeomorphism group of some new manifold Z1. Okay, so my apologies. There's a lot of superscripts and notations. I tried to kind of pare it down for the talk. Okay, so let's build this Z1, and for the building the Z1, we need a little bit more that comes out of the proof of the stabilization result I quoted above, which is that in both of the manifolds X0 and X1, or let's put it this way, you can choose your manifolds X0 and X1 to have this extra property. What you want is an embedded torus in each of them. Say X0 is maybe the, okay, say the manifold X0 that is non-trivial in homology, has 0 self-intersection. So, you know, for those of you who are up on your Gumpf and Substich, you know, maybe think of these, the X0 and X1 are sort of built out of, in the case at hand, are built out of elliptic surfaces. So you might think of this T as being a torus fiber as in an elliptic fibration. And all of the isotopy and all the interesting stuff that I referred to above all happens away from this torus. So the isotopy between the spheres S0 and S1 takes place, you know, just misses T altogether. So you can just leave T sitting there. Okay, so we need that additional property. That doesn't follow for free. That you have to you know, you have to prove the stabilization result correctly. Okay, so you take this a sum along this torus. So what does that mean? You take 2 copies of Z and glue them along a neighborhood of the torus. So this is kind of like fiber sum, and in this case, actually, it's more or less a fiber sum. You're just gluing using a certain diffeomorphism of the boundary here. So this is kind of my picture of Z. And notice it's kind of got 2 copies of this N. So it's sort of twice stabilized. It's got a copy sort of from the left copy of Z, and it's got a copy of N from the right copy of Z. Okay, so there's 2 copies of N. So here's how we create a loop of diffeomorphisms. So well, this is it's kind of here's the shorthand for it. It's alpha 1, and it's going to live on it's a loop of diffeomorphisms on this manifold Z1, and it's sort of a commutator. So what does that mean? So as I say, there's two copies of n, one on the left and one on the right. So let me actually, yeah, I think I get to scroll down here. So if we use the right, and the point is you can use either of them to stabilize the diffeomorphism. So if we use the right copy, so we sort of think of alpha on this side, and now we've added this n over here on the right, we can stabilize alpha connected sum with the identity of z, because we stuck in this n over here. Okay, so that gives me an isotopy that's, well, I mean, it's somehow, it's sort of wandering all over the manifold. I mean, you know, as you do the isotopy, things move back and forth, but I think of that as somehow coming from the left. So that's somehow the f, that's an isotopy f0. And so here's my loop alpha 1. It's given by, so I have to tell you, you know, for each t, I have to tell you a diffeomorphism. And I want at t equals 0, I want it to be the identity, and t equals 1, I want it to be the identity. Okay, so I take f0, this isotopy, somehow sort of more on the left, composed with the identity here, and then f0 inverse sub t, composed with this alpha, it's really alpha on the right. Okay, so what's going on there? Well, as I say, that's sort of, so notice that so the isotopy is somehow over here, the alpha is sort of, or the endpoint, alpha is the alpha on the right. And let's just check that it in fact defines a loop. Okay, so if t equals 0, well, it's the identity, and the identity commutes with anything, so that commutator collapses. If you take t equals 1, well, although the isotopy sort of wanders all over the place, at t equals 1, you're just doing alpha on the left, and it commutes with alpha on the right. So the commutator is the identity. So again, that defines a loop. Okay, so that was say a lot of years of struggle to come up with that observation. Trivial to verify, but as I say, it took a while. Okay, so that's the construction, and well, so we're going to show that that's of infinite order in. So the theorem is that that's of infinite order in pi1 of this diffeomorphism group. Finding the large subgroups is just kind of an elaboration of the technique, and I won't go into that so much. And I think I will not, because I don't want to overdo things. The higher homotopy groups are done in a similar way. As I say, what I just showed you was how to go from pi0 of diff, in other words, that interesting diffeomorphism alpha, to pi1 using this kind of commutator construction. And in fact, once we got from pi0 to pi1, the rest was rather similar. In other words, you're good. So this z has got not just the one torus to use for torus summing, but another torus to use for torus summing, and we could do a threefold torus sum. So if you like, if you wanted to go say from pi1 to pi2, you would do a threefold sum. So that's sort of 3 copies of z, and notice that that's got 3 copies of n, and we can essentially repeat the same trick. So I won't elaborate with what this by unwinding the formula the way I did above, but it's essentially the same trick. You use the isotopy that, so it's basically all the same isotopy. That isotopy is you know, you're using over here. I mean, it's a diffeomorphism supported here. You use one of the other, maybe the second one of these ends to create the isotopy F1, and then you do this commutator. And when you do that, what you see is that by a similar argument about what happens, you know, basically you're working on a square and you just sort of keep track of what's going on along the boundary. When you do this commutator construction, what you see is you get an element now of pi2 of diff C2. And you could just iterate that construction. And the interesting point, or an interesting point to me, is that in each case, we never, I mean, in some sense, you might say, well, maybe you have to think about how you take an element in pi k and of some manifold and then trivialize it in pi k plus 1 of this stabilized manifold. Well, that would be hard. I'm despite the fact that I've listened now to many people give wonderful talks about homotopy groups of diffeomorphism groups, I find it hard to keep track of all those parameters. But so the thing that's really going on is that all of those stabilization results that you need to go from pi 0 to pi 1 to pi 2, they're all based on this, on just this one isotopy. So how that single isotopy is responsible for all of the same stabilizations. So that's helpful, or at least it's helpful to me, because otherwise I don't think I could keep track of it all. Okay, so I guess this is sort of, I think if you like, I'll come back to this slide, but it's the same procedure, just iterated many times, and that's the way I've said it. That's going to give us a sequence of elements in pi 1, pi 0, pi 1, pi 2 of different manifolds, Z1, Z2, etc. And as with just a little bit more technique and a little more ingredients from four-manifold theory, you can find independent, summands of a given rank. You just have to, in some sense, you just have to add more manifolds together. Okay, so well, I haven't left myself much time, but let me say just a word or two about how to detect such elements. And the brief summary is that, well, you detect the difference between manifolds using gauge theory. So we detect the difference between these elements in these homotopy groups using parametrized gauge theory. So what does that mean? That means, well, the usual gauge theory in the mathematician sense, that is to say, in the sense that Donaldson taught us to do, was that we should study the solution space to some partial differential equation having to do with connections and so on. And so here's the briefest of summaries of what that means. You choose a bundle. In this setting, it's an SU2 bundle or an SO3 bundle over a manifold equipped with a Ruberman metric, so a Ruberman metric and an orientation. And I remind you that a connection on that bundle has a curvature, which is a 2 form, and so the PDE is this equation that I've circled, which says that if you take that 2 form associated to the connection and apply the Hodge star operator, which turns it into a different 2 form, it changes sign. So that's a so-called anti-self-dual equation, anti-self-dual. And an important thing to note is that, well, the curvature is just this 2 form. It depends on the connection. Doesn't depend on the metric, but the star operator does depend on the metric. So this is a PDE, and the PDE depends on the metric. So in gauge theory, one studies the moduli space, which is the space of solutions to that equation for a fixed G, and then you're only interested in them up to sort of automorphisms of the bundle. Okay, so here's just a sea of words. If you take a generic metric, then this moduli space is a finite dimensional, that's already striking, manifold with an orientation, and the manifold has some dimension, which I'll just refer to, as D of P. And the D of P is some kind of topological formula coming from the index theorem. If the D of P comes out to be 0, then you get, well, as it turns out in the settings we're interested in, a 0-dimensional oriented compact manifold. Well, that means just a bunch of points with signs, so you can count them, and you get the Donaldson invariant, which is just the count of those points with signs. So you require, of course, the metric has to be sort of general. It has to be a generic metric, kind of in the sense of transversality. Okay, so here's the idea of higher parameter gauge theory. If suppose you cooked up a setting where this this sort of formal dimension was negative. Then what does that mean? Well, if you think in terms of intersection theory, that means it's like thinking of things that should miss each other. So that means that the moduli space should generically be empty, should be a dimension negative something. And I chose minus k plus 1 for a reason you'll see in a sec. Okay, so how do you take advantage of that? Well, suppose now I have a spheres or a map of a sphere into the diffeomorphism group. In other words, an element of pi k. If I choose a generic metric and just pull back that metric by each one of those diffeomorphisms, that gives me a map of, well, that gives me a k-spheres worth of metrics. Well, look, the space, or if you like a map alpha hat, I think I called it, to the space of metrics. The space of metrics is contractible, so that alpha hat extends to some other map into the space of metrics, which I'll call beta. And now notice this, that's a k plus 1 parameter family of them. So if I take the union of all, so what would you expect? Well, if I have something of sort of formal dimension minus k plus 1, and I take a k plus 1 parameter family of them, I somehow expect to count a zero-dimensional family, that occasionally, once for some isolated values of my parameter, I should get a non-trivial solution. So that's in fact, so formally we take the union of all the points in the points in the ball of the moduli space with the metric beta of y. Okay, so, and that one we expect to have dimension 0, and we can count its points. Again, you have to think about orientations, and the invariant of the original alpha is the number of points in this moduli space. So the proposition, which is takes a little work, but it's sort of follows from basic results, is that that's first off well-defined, it's an isotopy invariant, and it's a homomorphism. And so let me just close then really with the sort of essentially the main calculation, which is what this procedure was defined to produce, which is that if you take, well, okay, so this is my old result was that if you could apply this to a single diffeomorphism, and then remember that had as its origin two different manifolds, x0 and x1, with distinct Donaldson invariants. And so the D associated to that single diffeomorphism is just the difference, well, multiplied by 4 between the Donaldson invariant for x1 and x0. So that says that if we started our way back at the beginning with distinct manifolds detected by their Donaldson invariants, then this invariant of the diffeomorphism would be non-trivial. So that was my old result. And what Dave and I proved last year was that if you do this kind of suspension thing with this commutator construction, each time you go up a dimension, you just multiply by 4. So that one example at the very beginning just it remains non-trivial. We're changing the manifold at each stage, but each time we're multiplying by 4. So that says that we're still getting something of infinite order. So that's an argument that all those different homotopy groups for different manifolds are non-trivial. And as I say, the rest is just sort of just some technique. All right, well, there's more to say, but let me just stop and say thank you very much for listening.
That's great.
All right, any questions?
Can I have a short question? It's Piotr.
Hi, Piotr.
So when you pull back some fixed metric, right? And if you change this metric, why don't you have solutions escaping through this sphere? Why do you have a well-defined invariant?
Yeah, you have, well, so yeah, that's a good question. Let me, because the proof already is that your question is very good. So you're asking if I have different metrics. Yeah, so let me see if I can draw a picture. I'll do it for the simplest of the invariants. So suppose I have, so what was our picture? So we had some initial metric, maybe G0, and now I have alpha star of G0, and now I connect those by a path. And what's my invariant? By definition, my invariant says that I should count points as I go along this. Okay, so now, so the key observation is, so now suppose I say, well, I take I just did it in the wrong order, but I take a G1. So you want me to take a different metric, right? And now I take a G1, and well, of course, those are connected by some path GT. And what am I supposed to do? Well, I'm supposed to take this, if I get my color scheme working here, I should take alpha star of G1, and now I can connect them, and I should count points on that side as well. Well, so the answer is, so I want to fill in this square, so to speak, and the idea is that I should take, so I have to connect alpha star of G0 to alpha star of G1. And here, what I'm going to take, not as an arbitrary path, but let me take here, this is an absolutely essential point. I take alpha star of GT. All right, so now what would I do? I say, well, okay, we're in the space of metrics, that's contractible, so I can fill that in with a two-parameter family of metrics. And now let me look at the two-parameter moduli space. Well, if you count the dimensions, that should be one-dimensional. But as Piotr points out, there's this sort of danger, which is to say, what happens if, so, you know, I start off, maybe I start at the top, and I follow some solutions, and, you know, maybe these kind of this is the classic picture, like for intersection theory. But what happens if like something goes off the side here? Well, the main point is that if I take the moduli space associated to the whole one-parameter family GT, this is diffeomorphic to the moduli space. Oops, we'll carry it away there, for the collection alpha star of GT. So if you like, whatever shows up on this side shows up on this side, and then it just keeps on going, and there's a one-dimensional cobordism between. So what is this red thing? What I see is that I get a cobordism between the moduli space of the yeah, sorry, I know this actually has a notation, but I don't want to get confused between my S's and T's and the moduli space that sort of interpolates between G1 going to alpha star of G1. And so therefore the count at the top is the same as the count at the bottom. So the argument for the other invariants is very similar. It's just you have to draw a two-dimensional picture, which gets a little bit messier. But it's the same point, which is that sort of the sides, whatever is happening on the sides, which, as you point out, could cause trouble, the sides kind of correspond. And if you think about the way the orientations work, what I'm really saying is that essentially this point and this point kind of cancel each other off. Or if you like, you could kind of wrap it up into a tin can, and then it's just a circle at the top and a circle at the bottom.
Okay, thanks.
Yeah, thanks. Great question.
I have a question. This is Dave Gay. So I don't know the right homotopy theory way to say this, but there's a weaker version of being homotopic, which is sort of being homotopic through pseudo-isotopies or being concordant or something like that. I mean, yeah. I know what that means for pi 0, but there's presumably some pi k version of that. Do you know anything about how your examples relate? Like, are they concordantly null homotopic, if that makes sense?
I think, what I really need to do is to humiliate myself in the presence of someone who understands this stuff well. I think the answer see the original alpha that I said is concordant, so it's homotopic to the identity, and it's a theorem of what's sort of separately due to Craig and to Quinn. That's actually the predecessor that says that that in fact those are concordant, or as some people would say, pseudo-isotopic. And by the construction that it's made, I believe that whatever the correct thing to say that you're asking about, that kind of you just build the pseudo-isotopy and you do the sort of same kind of commutator construction using that, and build the kind of it. There's what's known as the pseudo-isotopy space, which is the space of diffeomorphisms of, well, it's sort of built out of the space of diffeomorphisms of your manifold. Well, a pseudo-isotopy is this diffeomorphism of the manifold across I, and as the pseudo-isotopy space, you study the diffeomorphisms of the manifold across maybe a cube or a disk, again, REL boundary or REL some portion of the boundary. So I believe that it's kind of trivial in that setting. By the way, I should have said, I didn't say in my discussion, those elements that I created are trivial in pi k of the homeomorphism group, and that's how we prove it. It's again, nobody knows, as far as I know, much. I don't think there's any analog higher parameter version of the theorem of Quinn and Perron that says that allows you to conclude right off the top that elements in pi k of the homeomorphism group are trivial. But because we have a topological isotopy right at the beginning, you can use a similar commutator construction to do that. So all those results, so it's the same sort of trick, which is to say we promote whatever we know by either by construction or by hard theorems of other people. We kind of promote it up through the dimensions by this commutator construction. So I think the answer to your question is that you do the same thing, but I'm not entirely sure what question I'm supposed to be answering. So yeah, when that's supposed to,
yeah, me neither. That's why.
If you look on page 47 of our paper after the bibliography, there's a little list of things to do. And anyway, that's about number 4 on the list of things to do.
Great, thanks.
Perhaps for the sake of the recording, I'm going to stop it now, and then we can ask more risky questions afterwards. Okay, so let's thank Danny again.
Thank you.